I hope you got a good first overview of like what you can do, like the basic functionalities of accessing data. And now this is all something that you could do pretty easily by just downloading the raw data. It's much more streamlined. Maybe, as you saw, you can just put in the parameters you want and you get the data immediately. You don't have to search and then download an entire tile. Instead, you can download just the area of interest that you're interested in for the time period that you're interested in at the resolution that you're interested in immediately. And what we want to do now is take it a bit further. We want to do a lot more processing in the cloud and to make it really worthwhile to have this access to the streamlined data access, basically. So the way we want to do this is by showing a use case for measuring nitrogen dioxide concentrations. So probably a lot of you already know which satellite we're going to look at. You look like you will know. Sentinel-5P. And we'll also look at, because this is a Jupyter Notebook workshop, we'll look at how this slots into pandas. So pandas is a very popular tool for working with tabular data, so kind of like Excel in Python or on the Jupyter Lab environment. So we'll see how this output of the access slots into pandas. Maybe first, who has worked with pandas before here in this room? Show of hands. Okay, a few. So. Okay, so let's start with this. You can open the next notebook. So in your folders, if you go to BiDS Jupyter, there's the second one, 2 pollution statistics. And if you open air pollution statistics, the notebook, it should take you to this. And then we can just head right into it and look at air pollution statistics. So first of all, let's import all of the data that we need. First of all, change the kernel, otherwise it will complain again. So select kernel, Sentinel Hub. All right, and then it should not give you any errors. If there's errors, raise your hands and Mega will hopefully help you, be able to help you. All right, now, because we already did this step, we don't have to run this cell again. So really, you do not need to run the cell again. You gave it the name of CDSE, and we can copy that and just immediately call the config named CDSE. So in this shconfig with the profile name, we can replace this with CDSE and run this, and everything should be fine. So don't run the first cell. That's only if you haven't done the first notebook yet and haven't entered your credentials. If you run the first cell again, you have to enter your credentials again. If everyone is there, then we can keep going. So now we have a look at the eval script again. So the first eval script that we're going to look at is just a very simple one. We just want to get the raw data of NO2. So it's very similar to the eval script we did before for the true color, for example. In the input, we just specify the band that we're interested in, which is NO2. Output is float32, so floating point numbers, the raw actual values that we want to get, and a simple mosaic. And in evaluate pixel, we don't do anything, we just immediately return the NO2 values. So this is a very simple one. The next one will be a bit harder or more complex. So if we run this, we get the eval script, and then in the next one, we specify the request again. So this should also be familiar to you by now. We have the bounding box. This is all of Europe. Because Sentinel-5P data is quite coarse, we can get away with getting data for all of Europe. Then we define the data collection. In this case, not Sentinel-2 anymore, it's Sentinel-5P. We define the time interval. And the output type is just a TIFF. Bounding box of Europe, the resolution, quite coarse, as I just said, 5.5 kilometers by 3.5 kilometers. of pixel size. And then if we run this, get the data, this will take just a second. And in the next cell, we open up a country's shapefile, just to have an overview of where we actually are, that we use to plot it. So we get the borders of Europe from the ever so popular Natural Earth dataset and plot that data. And we can see the output. Anyone, did I lose anyone yet? All good? Okay. So in the output, we can see it's quite patchy. And that's just because of the nature of Sentinel-5P data. Everything that is cloudy, everything where the sun angle, like in the more northern latitudes, in winter, for example, where the sun angle is too extreme, is not be able to give you any data. Anything with snow cover will not give you data. So here, for just one single date, we can't see much. We can see Paris, the big plume of Paris, of just the traffic. We can see London, Benelux in general, the Po Valley, maybe over here Istanbul, but it's also quite patchy. And so what we want to do now is actually do a mosaic. So we want to get the mean data for an entire month of the NO2 concentrations. So get all of the data for an entire month and plot just the mean data as an image to get an overview over like a longer time period. And this is now really where this kind of eval script shines. So I'll run you through the eval script. And if you take anything away from it, maybe this, that mosaics and mosaics over time are very easy to get with this kind of approach. So here again, the setup, we get NO2, but also we now have data mask. So data mask basically tells you it's a binary mask, 0 and 1. 0 for everything that is no data or outside of a tile, and 1 for everything that is data. So in this image, everything that is white would be 0 in the data mask. Everything which has data is a 1. And here we also say mosaicing orbit. So instead of giving us just a single value, it will give you an array of all of the values in your time of interest. It will give you all of the values as an array. And so you can do a bunch of things, for example, making a mosaic per pixel, getting the mean value per pixel with this orbit mosaicing. So here what we do is we define a function which is clear, where we just check if data mask is 1. If it's 1, it's a clear pixel, and that should be good. With this, we take out all of the pixels that are not valid data, and then we sum all of those pixels up. So we just have a sum function where we sum over all of the pixels in that array. And so our evaluate pixel function is quite simple in the end. Remove all of the cloudy or otherwise no data pixels, calculate the mean by getting the sum of all of the remaining pixels, and dividing that by the length of all of the available pixels. And then the only thing that we return is the mean. So we go from, because Sentinel-5P is daily data, we go from a stack of 31 values just down to one single value. And all of this, of the eval script, is happening in the cloud, so this is nothing that will happen on your local computer. So if we run this, it will take a bit longer, the request. So we are just making a request for December of 2022. Same everything else, just the time frame, time interval changed, and the eval script changed. If we run this, the request will take a bit longer because it's crunching quite a bit of data. And then we can get a monthly mosaic of that data. And just for comparison, if we do it the traditional way, where we would download the netcdf files from wherever of NO2 data, you would have to download at least 17 gigabytes of data. And in this way, you just have to do, I think, a megabyte or something of the actual mosaic is going to be transmitted to your local Jupyter notebook. So this is really the power of an eval script and running that kind of analysis in the cloud, that we don't have to do all of this. So here is our output. Didn't take too long. And we get a much more complete picture. We see Madrid. We still have a bunch of missing data because it's December, as I just said. The sun angle is so low that the northern latitudes are either snowy or there's not enough sun up there to actually get any valuable data. The same for the Alps, just too much snow, and the Pyrenees. But for everything else, we have quite valuable data. All right. Everyone's still following along? More or less? Good. So what you can also try yourself, and maybe we'll skip it in the interest of time right now, but you can also do the same request and just change the time of interest. For example, you can try making a weekly mosaic or, I don't know, a yearly mosaic, but also be aware that this processing, you get a certain amount of free processing units per month. It's 30,000 processing units for a free user per month. And making a yearly mosaic is quite a good way to burn through all of your processing units. So be careful, but maybe you can try it out. It's definitely possible. It should be possible within your allotted quota per month. So what we want to do now is actually do some statistics. And we want to do some spatial statistics. And there's also two ways. I'll first show you the kind of naive, or the way we used to do it is by rasterizing a shapefile. In our case, we want to get statistics per country. So for each country, we want to see, okay, what is the mean NO2 concentration for an entire country? So we rasterize each country, give each one a unique ID that we know, okay, 1 is Austria, 2 is Italy, and so on. And then only take the pixels where those 2 IDs match, or with 1 ID matches, and calculate the mean from it. And that's what we're doing here. So we're here basically with features rasterize, we are getting our countries shapefile that we opened earlier, the geometry and the ID, so that's just the number. And we are transforming that with this country array into an array where it's just the numbers that correspond to the countries. And then we have 2 helper functions that are kind of pandas functions, where we first get all of the values that correspond to a certain ID, country ID. So everything in that country ID that is corresponding to that country array that corresponds to this country ID, we got all of the data from the raster that we just requested, our mean mosaic raster that we just requested. So if we do that, and then we calculate the mean for it over here. So get all the values and then calculate the mean. And we do this for each of the countries. So countries.apply, we apply that function to all of them and assign that to a new column in the shapefile or in the GeoPandas data frame, which is countries mean. We get an error because there's some countries where there's no data at all, or not an error, it's a warning, but that's fine. If there's no data at all, we'll just ignore it. So let's quickly look at what the data looks like. If we just look at countries, this is kind of what it looks like. Vatican doesn't have any data. And we just have this mean value at the end. So Morocco, a mean NO2 value of this. Netherlands, a mean value of that. And now what we can do, we can sort it by this column. So sort values by the mean column. And we can print out the top countries with the most, the highest mean NO2 concentration. In this case, it's the Netherlands. Anyone here from the Netherlands? You won. Followed by Belgium, Estonia, and Germany. So what we can also do is we can plot, to have a better overview of the actual distribution, we can plot a box plot of all of the values in a country, all of the NO2 values in a country. So that's what we can do here. And this is basically the distribution that we get. And this is pandas workflow now. It's just how you would do it with pandas, more or less. And here we can see a more complete picture that the Netherlands definitely has the highest mean. But in Germany, if you're unlucky, you live in a city with a lot higher NO2 values. All right. So this is kind of the approach you were doing it, basically, how you would usually do it. And then there's also another approach with the statistical API, which I'll run through next. And the statistical API is basically this whole process that we went through now, where we first get the entire raster data, then we rasterize our vector, we get all of the values that correspond to each one of our vectors or each one of our geometries, and then we do some calculations on those values. All of this can also be done in the cloud or with the Sentinel Hub APIs on CDSE. So right now we did it all locally, so we have to get an entire raster, and we can also go straight, without even having to download the raster, we can go straight to just that one value that we want, the mean, without having to download anything else. We just left off at the spatial statistics, calculating spatial statistics, doing it kind of the old school way. And what we want to do now is doing it the new way, or the more streamlined way. And to do that, we want to look at a time series of EU capitals, also to get a more complete picture of NO2 concentration over an entire year, because right now we only looked at December, which maybe isn't quite as representative for a whole year for all regions. So we want to do this with the statistical API that Anrash already kind of mentioned and Mega also mentioned. And for that, we first load our new vector data, which is the capitals in here, load capitals. And then there's a small kind of try it yourself block where you can enter your own like coordinate of interest that you might want to see an entire year's worth of NO2 data. So if you know your coordinates of your hometown of something by heart, you can just enter them in, or you can go to a website. I linked just one website where you can get lat-long coordinates there. If you don't want to do this, you can also just keep it at the default. We picked Faro. It's supposed to be like that's in the south of Portugal. And it's supposed to be one of the cities with the cleanest air in Europe, which makes sense because all of the fresh air from the westerlies from the Atlantic come in to Faro, basically. So if you've picked your desired latitude and longitude and input your name, that's being inserted into the data frame, just your custom point, and with the column name and the geometry of the lat long, basically. If you don't have any coordinates ready, or if you don't want to change it, you can just keep it like that. So let's enter that. And now let's have a look at the evaluate pixel function, or the eval script function for statistical API. It's very similar to the one for the processing API, but there's one major difference, and that difference is kind of due to the fact how the data has to be processed. For example, for Sentinel-5P, there's a lot of no data values, so I don't know what exactly the no data value for Sentinel-5P is. Mine is, I think for Sentinel-2, it's minus 32,000 something. Which we don't want to include into our statistics. That would completely skew our statistics. So we have to tell in the eval script which pixels should be included in our calculations and which pixels should be excluded. And so for the output here, you can now see we have two outputs now. We have the default output, where we just output, or which we name NO2, and we have another output with the ID data mask. And we have to give this data mask output to tell the backend which pixels to be included. So basically, if a pixel where the data mask is 0, it will be excluded from the calculations. If it's 1, it will be included. For this one, it's quite simple because we can just use the data mask that is provided directly. For Sentinel-2, for example, if we want to exclude all the clouds, we would have to construct our own data mask from the scene classification layer, because the data mask that is included, because cloudy pixels are valid pixels, will not give you straight away a 0 for a cloudy pixel. So that's just something to be aware. In this case, it's very simple, but for Sentinel-2, for example, you'd have to construct your cloud mask to say, okay, don't include the clouds into our statistic calculations. And then the return down here, we have the default output and the data mask, which is just the data mask that we input. This is basically just to check if the value is valid or not. You can even omit it, it should work just as well, just fine. So now what we want to do is we are building a request for the statistical API. And it's also very similar to the processing API, but in this case we also have the aggregation. And that's a feature of the statistical API, which makes it very easy to get time series. So we input our time interval. For this case, we are doing all of 2022. So from the 1st of January 2022 to 1st of January 2023. And then this is kind of the quite a powerful thing. We'd given aggregation interval. So P2D means every 2 days we want to have statistics calculated. We could even change this to P1D, and then for every day we will get a value back. In this case, P2D just to make the request a bit quicker. I'll actually start running that already because this tends to take a bit of time. And this can be changed also to P1W, for example, for 1 week, or P1 month, 1M. So you just get a value per month or a value per week. You have to keep in mind, though, here it will just take, it's a simple mosaic, it will just take the first value that you get in that 1 month, basically, the most recent value in the time interval. You could also replace this kind of script with the mosaic. So then it will do a temporal mosaic for the aggregation period, and then will give you the mean value over that temporal mosaic. In this case, it will just give the first value, which might be cloudy or no data. And then our size, because we're only interested in like the time series of points at the moment, is just 1 by 1 pixel. So let's define that. I already did it. And here we define the request. So for each geometry, for each point, we do a small buffer just to make it bigger. We define the capitals that we get. In this case, we get all of the capitals of the top 4 most polluted countries in the analysis we did earlier. So Amsterdam, Brussels, Tallinn, and Berlin, and our custom point. In our case, it's Faro. And then the central hub statistical. So for each one of those capitals, we make one request. So for each one in the selected capitals, we do one request, and we append that to the requests list. So bounding box is just the bounding box of the shape. Aggregation is the aggregation we defined earlier, input data, Sentinel-5P that we also defined earlier, and that's basically it. And then this Sentinel Hub statistical download client will just download all 5 requests in parallel. So for me, this cell already ran. I hope for you as well. And we can just have a look at what kind of output we get from it. Because it's a web API, it will give us kind of a format which is very web readable. In this case, it's a JSON format, basically a dictionary. And we have data and then the interval, and the interval from and to. So in this case, 1st of January to 3rd of January, that's our 2-day aggregation period. And in those 2 days, we have the minimum value, the maximum value, mean value, standard deviation. Because for us, we only have 1 pixel, all of those values are basically the same, or standard deviation is 0, because we only have 1 value. If we have a bigger area with more pixels, it would give us the minimum, maximum, mean, standard deviation for all of the pixels in that area. So now, because this isn't very, we can't handle it very well in Python, we want to convert it to pandas. And this is done here. And the big one is this JSON normalize. It will take a JSON input and it will output it into a pandas data frame. So for our output, the object data, we get for each one of the capitals or each one of the points, we get all of the data that is in there and make for each one a separate data frame. And then for each data frame, we assign it the correct capital or the point, the name of the point as a new column. Then we put them all together. We simplify the column names a bit. That's just data cleaning, and you could also skip this step. But then we have like very long column names. And we convert all of the numeric columns to numeric because that wasn't done automatically by this normalization. That's basically it. We also say we do a new column month, which we want to aggregate over later, and save all of that to CSV. And this is kind of what the data looks like now. We have the from and to column, minimum value, maximum value, mean value, standard deviation, and the name of the point, together with the month. And with this, we can now do, because this is a pandas data frame, we can do all of the analysis that we might want to do. So for example, just for this, we'll do a line plot over all of the month and see how the NO2 value changes over the months for all of those points. So this is what it looks for me. Up on top, we have Brussels, which seems to be highest overall over all of the months. And then all the way at the bottom, apparently it's quite true that Faro has very clean air, is Faro with very low values. I don't know how it looks for your points that you might have selected. Maybe, hopefully it looks good. Still running? Okay. Hopefully it runs through. But so what you can also do is you could do the first, like maybe as a try it yourself later if you want to dive deeper into this. You could try the first analysis that we did with the different countries and getting the mean for a country. This can also be done in this way, basically. So you could, up here, change the input shapes, basically, and change them to the shapes of the countries. You also have to change the output size, and then you would be able to do the first analysis that we did and get basically the same results as before. All right. It's still running, or did it finish? It's still running? Okay. Yes?
Sentinel-1, how this pre-process is done. So for example, I can access Sentinel-1 data, but usually when I work in local, I have to pre-process it and make some calibration, apply some data derivation model for correct connection and so on, which is the default processing of this data. Is documented for all this data?
Okay, so the question was if for Sentinel-1, how you would do the pre-processing to do the statistics. So the pre-processing for Sentinel-1 that is necessary before you can do the statistics. And for Sentinel-1, a lot of the pre-processing steps like terrain correction, speckle filter, that's available as parameters that you can specify in the request. So we have a page. Wait a sec. So under support, we have the documentation portal. And here, under APIs, I think, Sentinel Hub, you have the data. And here for Sentinel-1 GRD, you can see all of the available processing that you can do. Here, processing options, auto-rectify, radiometric terrain oversampling, spectral filter, backscatter coefficient. And if you would want to do something more, then you can see if you can do it in an eval script. Otherwise, you'd have to do it locally then.
So you can define some of the parameters. And the Sentinel-1 SSE is not at all supported?
At the moment, no.
And it is in the roadmap, or what do you say at the moment?
I'm not sure actually if it's in the roadmap. I think it's quite difficult to get it into a format that is very efficiently. Sorry? The GRD data is available, yes, but to elaborate the data is completely different. Yeah, it's hard to get it into a cloud-optimized format, and so that's why it's not available. But yeah, GRD data is available. All right. But yeah, so kind of what we saw here is how to do this spatial statistics in the cloud and how to, in theory, do it much more efficiently. Also something to mention, if you want to do that for quite a lot of vectors. So if you have, for example, if you're an agriculture company and you have a lot of different fields that you want to monitor, because one statistical API always works for just one geometry, you can also use the batch statistical API. This will do it for all of the geometries in the cloud asynchronously, and it will deliver it to your bucket. And it's much cheaper also to run this batch statistical API than the normal API.